right? So, copper 2 sulfate and sodium hydroxide, right? That's our reaction. When you see it first, I want you to write down your reaction. Courtney, what's the reaction?
It is CuSO4
Okay.
plus OH.
Okay.
CuOH2.
Good. Na2SO4. Okay. Who's our precipitate? This says precipitate out all of the hydroxide ions, so who's the precipitate? Right, it has to be the hydroxide because it's the one that's precipitating. And you know sodium, all group 1 is always soluble, right? Doesn't matter what it's paired with. Ponies, dinosaurs, kitty cats is always soluble. Balancing it, what we need 2 here. There we go. All right, so if I wanted you to write the NIE for this, and you know that when I give you solutions in the beginning, the 2 reactants are always aqueous, and the precipitate's forming, and we know that last one is also a soluble salt. So what you're thinking about is that these 3, basically, this is a soluble salt at this point, SS, soluble salt. This is a strong base, right? We know it's ionizing. This is a soluble salt, so it's ionizing. If I wanted you to write the NIE for that, you could go ahead and write out the entire total ionic, and then the net. But can we jump straight to net? So knowing that all these are soluble, except for the precipitate. What's the net? So this one, 2 plus and 2 OH is right. That 2 coefficient does distribute. And you know, sodium cancels, the sulfate cancels, sodium sulfate over here. Okay, and then this precipitate stands alone, right? It stays as is. So I know sometimes it's going to be really easy to write the NIE from a pretty easy reaction, but today we're going to get into some that have weak acids, weak bases, gases, pure liquids, so it's going to get a little bit more complicated. So don't depend on not skipping the total unless you need to. All right, so the question, what volume of that is needed to completely precipitate all that out of that and that? Okay, what do you guys want to start with? Right, so the volume of the sodium hydroxide, and I'm going to do milliliters because I'm a milli person. Okay, what's next? We're just doing straight stoichiometry. No DDA table is definitely necessary here. I'm going to go straight stoichiometry. What's next? I need to do what? I heard convert to moles, but what do you mean? Use the molarity. Okay, so 4.39 millimoles of NaOH to 1 milliliter of its own solution. So the milliliters of that solution cancel. Okay, what's next? Remember, we don't care about sodium hydroxide. What are we going to? We're going to the question, what volume of copper 2 sulfate, right? Question is milliliters of copper 2 sulfate. That is our question. All right, ready when you are. So we're done. We got some millimoles of copper or sodium hydroxide. Ratio, thank you. So it's a reaction, right? We're going from the one reactant to the equivalent amount or appropriate amount of the other reactant. That's what we had to balance it first. So the ratio is a 2 to 1, right? So 1 mole or millimole of copper 2 sulfate is used for every 2 millimoles of sodium hydroxide. So now we're totally done with sodium hydroxide. We've equated the the hydroxide ions to the millimoles of copper 2 sulfate we need, but that's still not the question. So what's our last step? How do you use it? On the bottom, so I'm flipping the molarity, right? Yeah. Okay, so that's because I need to get milliliters on top. So that fraction is going to go here. What was that molarity? 3.38. So 3.38 millimoles of copper 2 sulfate for every 1 milliliter, and then we have our volume of the copper 2 sulfate solution. So this one does not require BDA. You could, but I think you'll be working too hard on that one. This is going to be basic stoichiometry. It's not a limiting reagent problem. And whatever you guys get. So like 200 divided by 100 divided by 3.8, like 30. So I just approximated, but that's what it's 29 point what? 6 milliliters. Okay. All right. So if you can do that on your test, right? Not a hard problem. I just want to give you more sample. All right, so notes from last night. The definitions. What were some new things for you guys? Definitions and conjugate acids and bases. Allie. Say again? Amphoteric. Yes. Okay. That term, you did learn amphoteric, but tell me what's it called when someone can write with both their left and their right hands? Ambidextrous. That's that one, right? So that's basically the same thing. Amphoteric means that you can act like an acid or base. So that's just a term to know. So give me an example of an ion that can gain an H plus and also donate an H plus. Give me an ion. I know, so we know that water is that chameleon, can go both ways, right? Because it can either gain an H plus to become hydronium, or it can lose an H plus to become hydroxide, right? Give me an ion. But it's got to have an H to be able to donate, right? Diphosphate, right? Okay. So HPO4 2-, right? Can gain or lose. Yeah. HS minus, right? So that can gain or lose. So as long as it has an H to give, that's good. And you know, as you can probably see here, if it's going to gain an H plus, it might have a negative charge already because it's going to take on the H plus to become neutral species. Or like water is just naturally able to donate because it has 2 H's available as well. Okay, so that's just a term, amphoteric. Okay, so thanks, Allie. Something else that was new for you. Did you hear my bad acid talk? Okay, you just got to deal with that. I have to come up with silly ways to remember things. Bronzo-Lowry acids, Bronzo-Lowry bases, conjugates. Okay, let's just kind of just do a quick check. You have your notes out in front of you. That's totally fine. Log on to Socrative for me. This won't take you, but hopefully 5 minutes. It is 10 multiple choice questions. That is it. I just got to turn it on. 1 second. You know how to get back on there, Socrative? It's when you Google Socrative.com, it'll be student login. Then you get on student login, you type in the room name Enlo. If you guys want to download the app, that's fine, but just maybe later, not right now. And it's been started, so you can go ahead and log in. It won't take you very long. So if you're right next to somebody, if the questions are scrambled, it's okay. But you can use your notes. You took good notes, and I want to reward you for that. You guys to focus on finishing the videos and doing the notes that I've provided for you with the videos, that packet. There is an additional problem set on my website. I'm not requiring you, be quiet. I'm not requiring you to do the extra problem set on my website unless you're like, oh my gosh, I really need some more practice. If you want to, you can do that for study evidence before the test. But don't sweat that right now. Get through just exposing yourself to organic, and I'm good enough with that right now, okay? So, a couple of rules of thumb before we start the acid-base NIEs. You did your you talked about the strengths of acids and bases already. So I'm going to go through a couple of these things quickly so we can do about 10 examples. And then I'll tell you specifically what I want you to do for homework. Because right now I have odds of something. I'll tell you that in a second. Okay. So whenever it says you have 2 solutions coming together, those solutions are soluble. We're going to say that solution is the appropriate concentration so that those things will ionize. So at the very beginning, when it says solution of sodium hydroxide and a solution of lead 2-phosphate or something like that come together, that means that they will be soluble. Second, you will never, ever ionize weak acids and bases because they do not appreciably ionize. We will not separate them in NIEs. So they're always written like as their entity. So if I say acetic acid, a solution of acetic acid, will you ionize that? No. If I say a solution of hydrofluoric acid, will you ionize that? Hydrofluoric.
Oh, no.
No. A solution of hydrochloric. Yes. So think about that as we're writing them. And so another thing, you guys are going to start to mix up all kinds of NIEs. We're going to do decomposition, synthesis, single, double, combustion, acid-base, hydrolysis, neutralization. So all these things are going to come together now. So you're like, oh yeah, sodium solid or sodium chloride is soluble. That's it. It's in solution. If I say powder, if I say solid sodium chloride, and you need to, for yourself, your own purpose, put that solid there. Will you ionize that? No, a solid cannot poof into ions. That would be really bad. The solids stay together. Solids do not ionize unless they're in aqueous solution. Okay, so we're going to work through examples with this, and we'll apply this as we go. I'm videoing for you as well, but I'm going to hit the highlights here. I give you guys a little bit more time as needed. So on here, the highlights would be nothing right now. I think I'm going to do the sodium sample. We'll talk about coordination compounds in a lab. I'm going to wait on that for a second. The hard thing to do with hydroxides, and I mentioned this in some people's labs yesterday, is that sometimes, you have those hydroxides that are soluble because they're exceptions to the rules. The ones that we generally say are exceptions are CBS, calcium, barium, and strontium are exceptions to the insoluble hydroxides rule. They're all slightly soluble, but the slightly soluble mean you ionize them or you don't ionize them. So I'm going to try my best in all my examples to stick to this one rule, and that is down here on the bottom. Let me minimize this thing real fast. Try my best to stick to this. Barium hydroxide and strontium hydroxide are soluble enough that they should be ionized. Because remember, it says hydroxides are all insoluble except for CBS, meaning they're soluble, they're ionizable. But we're going to stick to the differences because there is a difference between those two. Barium hydroxide and strontium would be ionized, whereas magnesium hydroxide and calcium hydroxide would be, they're so slightly, we would also call them essentially a precipitate. So stick with those. That's the weird hydroxide, like fence, you're on the fence about is it going to ionize or not. Give me a thumbs up when you have at least that right there, written as ions and then precipitating. Just going to memorize it if you're not writing it down. And they touch each other. So like magnesium and calcium are precipitating, and strontium and barium will ionize. Give you a second there. So you went through, so the next thing on notes are just the recap of notes from last night, but you guys did your notes, so I'm leaving that to you. But go ahead and tell me from here, this is a hydrolysis reaction, okay? From here, no, well, sorry, and why is that hydrolysis? So water is breaking apart the salt, yeah. Yes, we use the term ionize a lot when we say we're talking about NIEs and the ionic equation because we're talking about things breaking apart. It's the same thing as dissociate for that purpose, but truly the correct way to use ionize is with molecular compounds like acids, and dissociate goes with salts, and then dissolves goes with covalent things that don't really ionize or dissociate. So those have very specific meanings, but when I say it, we're talking about breaking apart now. Yeah.
We had a problem where we had a solution that was slightly soluble. How are we supposed to mathematically determine how much precipitate would be formed?
I will not ask that of you until we get to equilibrium. When we have an equilibrium reaction, when we can figure out using a KSP value. Wait, without 2 months on that, I'll let you know. Okay, so this is hydrolysis because it's a salt that's being attacked by water. It's breaking apart back into its original acid and base. Because an acid and base come together to make a salt. Well, ammonia, water makes ammonium hydroxide truly, but I went ahead because is ammonium hydroxide a strong base or a weak base? It's truly weak, right? But ammonium, this may have been by itself ammonium hydroxide, but sometimes this will ionize. Despite the fact that it's weak, sometimes this will ionize. I'm really only doing this not for the NIE purpose, but for the vocabulary. So as you can see, ammonia formed ammonium by the donation of an H+, right? Okay, so is this the acid or base? This accepted an H+, right? Base, okay. Oops, base. Bases form conjugate acids, right? Okay. And this water, knowing it's amphoteric, it can act either way, but in this case it acted as a what? As an acid, and it formed a conjugate base. The reason that these are called conjugate acids and conjugate bases is because if we went in the reverse manner, how would they act? If we reverse this process, the ammonium is acting as a what? As an acid, because it's donating its H+ back to hydroxide, so it's donating, it's a bad acid, so it's an acid. and the OH is accepting, so that's called the base. That's the only reason we call them conjugate acid base, because it's talking about in the reverse manner. And sometimes these are reversible if we're doing equilibrium examples. Okay, so down here, looking ahead and what's happened, what is nitric acid acting as? What happened between this guy and this guy? So it donated, we're going to use the word donate to kind of stay consistent. It donates an H+, so it's the acid, this is the base. Nitrate is the conjugate base, and hydronium is the conjugate acid. Okay, so we're okay with labeling the vocabulary using our conjugates with Bronsted-Lowry definitions. Oh, so hydrolysis reactions, they tend to always remake their acids and bases that the salts came from. So, knowing that, I can't do that with this example right now, actually. I'll hold off that thought. It's talking about the acidity or basicity of the end result. All right, so this is a strength chart. This is just from your textbook. But as you can see, we know these to be the strong acids, right? It says perchloric, iodic, bromic, chloric, nitric, and sulfuric. And we know that they 100% full arrow, 100% ionized to their ions. And this says Ka, and if you barely remember equilibrium, there's a K value. It's called the equilibrium constant. That K value greater than 1 means that all the products are favored, 100% favored. So these are favored, meaning the products of this dissociation are favored, meaning you will only have this. You will never have truly this unless it's in a powder form. In solution, you always have the ions. But everything else that's a weak acid, their Ka values, equilibrium constants, are less than 1. You can see that here as being a negative exponent. So less than 1 means that this equilibrium favors not the products, the reactants. So these forms and so forth are favored, meaning predominantly what's in the solution, this or this. The reactants, you're going to have a lot more of these combined versions of the acids than the ionized versions. But in the strong acids, you have a lot, like 100% of the ionized versions versus the combined versions. So that's really just reiterating again, weak and strong, what do those terms mean? But now we're relating it to something called the Ka value, which is the equilibrium constant value. Yeah?
What makes it being 100% ionized? Like, why is it stronger?
Because, so for example, when we calculate pH, the stronger acids always have a very, very, very low pH. Remember, acids are on the 0 side of things. So when I calculate pH, which is, does anyone remember the pH formula? Negative log of the concentration of H+. Do you remember that now? Okay, so that's a good question. I make a ton of H+, my pH goes way down. I make a couple of H+, my concentration's not high. So I'm going to be closer to like 4, 5, 6 on my pH scale, not 0, 1, and 2. Does that make sense? So that strength does relate to its pH as well, because you're making a lot of H+, or you're not. You're still an acid, you're just not making as many as the other ones are. Now bases work very similarly, but I'm going to stick with acids for now. Oh, and this is just that picture. HA breaks down to H+ and A-. HB breaks down into H+ and B- based on their strength. So this one breaks into a lot, we have 100% here. This one breaks into basically nothing. So if I give you a graph like this, and pictures like this, could you tell me since they're strong and weak? Based on dissociation and not, or ionization and not. Okay. Let's go to NIEs now. Oh gosh, now I have to do this. I have to show you this. So that K value I was telling you about, it's embedded in some of the calculations for pH, and you guys are going to watch, I think it's 10 minutes of the pH video tonight, basically how to review on how to calculate pH, which is a basic level of understanding from Honors Chem. And this is one of the equations you'll see. Do you remember doing that? K is equal to hydronium's concentration times hydroxide's concentration. It's on the reference sheet. It may have been a while for some of you guys, but basically, since water is amphoteric, it can go back and forth. Obviously, I'm just going to draw it one way. So this one donated to form hydronium, this one accepted to form hydroxide, so that's the amphoterism again. But amphoterism, in terms of water, when it forms ions, has another term that's associated with it called auto-ionization, meaning it self-ionizes. Water all the time will donate and accept an H plus. So a lot of times in water, we'll have a lot of hydronium and a lot of hydroxide, but if they're equal quantities, because it's a 1-to-1, what's the pH? pH should be 7, because it's neutral. If you have a 1-to-1 ratio, the hydronium is the acid that's forming, hydroxide is the base that's forming, and so equal amounts makes it pH 7. That comes into play whenever you see the concentrations are equal. So hydronium's concentration equals hydroxide's concentration, and those concentrations are 1 times 10 to the negative 7th. That plugged in here, 10 to the negative 7th times 10 to the negative 7th is 10 to the negative 14. Where's 14 relevant in pH? Okay, that's the extent of the pH scale, basically. So that's encompassing both the acidic portion of water and the basic portion of water, which is why it pushes the 14. It's not saying that the water is pH 14. It's just that's where that number is relevant here. And that's the KW constant, which is a constant we'll use. So if I give you KW, which you always have KW being 10 to the negative 14th, I could say, hey, here's the concentration of hydronium, find the concentration of hydroxide. So you can plug it into this equation. You'll see maybe a little bit more of that on your video tonight. So water is not the only thing that can act amphoterically. There's a base version of that, and it is ammonia. Ammonia, you can see it can do the same thing. It can donate or accept an H+, forming ammonium and an amide. It's just the name for that. And this is ammonium, you know that one. And so they can auto-ionize as well. And I was going to have you guys, I'm trying to shorten the videos because I say, oh, it's a 15-minute video, but if you're pausing a lot and writing a lot, it might take you longer. So this was on the video from last night, but I didn't want you to do too much because you were prepping for the lab too, which I appreciate. You're doing really well. Gives me exactly what you're talking about. I like that. Okay, so I'm going to next go over some NIEs, and I'll probably only get through a couple, and that's okay. Okay, so let's start with this one. Okay, I want you guys to write out your reaction. And we're going to think about how to ionize and how not to ionize as we go on. So let's kind of do this together as we go. Vinky, tell me the first, the reactants here. So potassium hydroxide, and you're assuming these are aqueous right now because I'm not telling you anything otherwise. This is a solution, okay, plus. Okay, Lucas, pick up the next part. So potassium hydroxide, nitric acid makes. And, right, and I'm just going to write that as HOH because that's sometimes better or easier to see it as a double replacement. So you have this K, which is a plus, this OH, which is a minus, this H, which is a plus, and the nitrate. Don't be a homewrecker, leave it together, keep nitrate together, and that's when we make potassium nitrate. So an acid and a base make salt and water. Salt is not sodium chloride, right? What's the generic term salt referring to? Anything ionically bound. Right, okay, so we have this nice ionic compound, it's a salt. So in terms of solubility, nitrates are always soluble, so I'm going to put AQ there. What's this? Well, what's its state? Liquid. Okay, this is not soluble in itself. Water cannot be dissolved in water, so it's a pure liquid. Do not ionize pure liquids. We ionize the K+, we ionize the hydroxide. Why am I ionizing this? Don't say because it's aqueous. What else could this be? Okay, so I would not ionize that if it were aluminum hydroxide. Strong base, right? So this is a strong base, so I'm breaking it up. This is a strong acid, right? So I'm going to break it up. So go for it. H+ and nitrate, okay, yields. This is a, not a strong base, not a strong acid, but a, it's a salt, right? We just talked about that. Is it a soluble salt or insoluble salt? Soluble salt. Okay, so I'm just labeling as I go, just so you know why we're breaking these apart and why not. So you first need to identify if it's a strong or weak acid or base. If it's a salt, you got to figure out if it's soluble or insoluble. And remember, you can only ionize the ones that are soluble or strong. And water is not going to be touched, right? So this is the K+, and then this will be nitrate. Water stays as it is, H2O liquid, What's the only thing left after spectator ions are kind of eliminated here? Right, so spectator goes away, K plus nitrate. You have hydroxide and hydronium essentially, and water being your final. You have that so many times with acids and bases, because that's what I mean. Strong acids and strong bases, their strength comes from the ionization, and everything will cancel except for the hydroxide and water. That's really one of the most important things about acids and bases. They combine to make water. Okay, so that one's easy because it was strong, strong, and soluble. Let's do the next one. So go with me here. Savannah, first, sodium hydroxide, NaOH, Arushi, nitrous acid, Chloe, one of the products, NaNO2, AJ, other product. Thanks, Levi. Okay. Now, identify. What do we have here? Strong base. I'm just going to put SB up there just for now to keep you thinking about that. Next, weak acid. Do we ionize this weak acid? No. Next. Next one. Soluble or insoluble? Soluble. Sodium, because we have a group 1 metal, and then this is pure liquid. Okay, so this helps you with this, just thinking of your process of how you approach these. So we know this one ionizes. I'm quickly ionizing these. Sorry if I'm going too fast, but I want to work through some more complex ones. I left this one alone. Why? It's weak. Do not ionize it. It does not ionize appreciably. And the next one's does ionize. So we're making sodium ion and nitrite, and then water stays as is. All right, so this is going to look a little interesting at the end. What's the only thing that's a spectator? Sodium. Anything else? No. Nitrite cannot cancel. So in the end, you still have hydroxide, nitrous acid, nitrite, and water. So tell me, in the end, as this reacted, because acids and bases, no matter if they're strong or weak, weak and strong, no matter what, acids and bases always react. They 100% will always react. The weakness or the strength of it does not matter. It will react. And you can see I'm drawing a forward arrow here, not a reversible one. It does react because the hydroxide is such a good base. It will force this H plus to be given to it to form water and leave nitrate by itself. It's just not going to do it until it actually reacts. That's where we're leaving it together until it actually reacts. Okay? You have a question? Gotcha. Okay. So, and I'm not writing the NIE, but you guys know when you would write that. All right, go ahead and do the next one by yourselves or with a friend. You have friends at the table? Make a friend if you need to. Got a product for me? Any takers? Product or products? You're like so quiet. It's okay if you make a mistake. We're all gonna be making some mistakes the entire year together. Let's go ahead and get started. Jacob, thank you.
Alright, one of the products that possibly is like nitrogen monofluoride.
Ooh, you're getting real crafty on me here. So let's think about if one is definitely an acid and one is definitely basic, right? Ammonia is a pretty good base. What could happen between them? Just an interchange of Kurt?
The hydrochloric acid could give its nitrogen to ammonia.
Okay, so to make it ammonium. Okay, so I'm good with that. So we know that acids and bases just do one exchange. So you're going to say ammonium and fluoride by itself, or which is what I think you were going for was ammonium fluoride, because what you might see is like, oh, this donated, but this fluorine in aqueous solution could maybe get together without to form a salt, because that's what acids and bases do, they form salts. But again, you have to consider this salt is actually soluble, and it should, being a soluble salt, ionize into those two things. Now, so you could have gone from salt and then ionized, or you could have just said, oh, it's an acid and base, donate the H, boom, boom, as this originally. So in the end, you're going to come up with the same answer. But in the end, ammonium fluoride being soluble, that's great. What happens with our NIE? What do we write here? HF. Okay, what do I write next? NH3. I can't ionize either of these because this is a weak acid and a weak base. So I have to keep those together for my NIE and just write these separate in their salts, ions. So this is my NIE right here. So if you had formed the salt first, you would have ionized, but you cannot ionize anything else. You with me? You good? Let's do one more, a little bit more, more complex one. I just gotta find it, so give me a second. There we go. Number 6. A solution containing 1 mole of phosphoric acid is added to a solution containing 2 moles of sodium hydroxide. Ignore the mole thing first. Let's just write the reaction, then we'll consider what to do. Reaction, what are my reactants? H3PO4, so phosphoric acid, and NaOH. Okay. Now, before we write our products, don't show me the products yet, because this one is very specific. We have a polyprotic acid with 3 protons. We have a base with 1 hydroxide. So truly, 1 hydroxide will only be able to neutralize 1 of the H pluses. But I have a ratio here that's been given to me. I have 1 mole of this and 2 moles of this, right? So how many H pluses will get neutralized? 2, because I have 2 servings of hydroxides to attack. So what does that leave me with here? So what's the ion? Okay, so biphosphate, so just HPO4, 2 minus. Okay, so HPO4, 2 minus is our anion. Who does it get with? It has to bind with somebody to make a salt, right? It's got to make the salt. So we have sodium biphosphate, right? Na2PO4. And we know that 2 of the hydroxides got with 2 of the H's to make how many waters? Say again? 2 waters. 2 OH's and 2 H's make 2 waters. Or 2 HOH's is that's how you think of it. So this one, it should be balanced once we put our 1 and 2 where they belong here. Because this thing have 2 moles of that, this thing have 1 mole of that. So this one only partially neutralized all the H pluses in that acid to make this salt and water. How would I write the NIE? Give me straight to NIE if you can. Ready when you are. What do I do? Great, nothing. Great, guys. Okay, so this is H3PO4. I was waiting for somebody to say something, but this is weak acid, right? Weak acid do not ionize. This way. So 2 Na pluses and 2 hydroxides. Okay, yielding. Does this ionize? What's your gut instinct say? Yes, but why? Because it's a group 1 salt. Group 1 salts, doesn't matter if it's bonded to a dinosaur, people, it is soluble. It looks to me like something crazy, and you're like, oh my gosh, what do I do? Sodium. Sodium is telling you, ionize me. There's 2 NAs, there's a biphosphate here that ionizes away from it, and then what do we do with water? Leave it to water liquid, and then the only spectators are the sodiums. So you have phosphoric acid plus 2 OH's yields biphosphate and 2 waters. Okay, so that's I think as far as I need to go right now. Do me a favor and pull out the, I guess it was like, well, it's your packet of work. And I'm going to tell you what I want you to do first. So I'm going to try, I want you guys to really just try. If you only get reactants down and some states of matter, I'm okay with that. But you're going to see that you're going to try the evens of 1 through 30. It looks like this is from the bottom of that page. From the bottom of the page it says AP chemistry practice with NIE, predicting practice without redox. So NIEs can really be embedded through many multiple choice questions, through stoichiometry, through ion concentrations, through titrations, literally anything. So I want you guys to do evens here. So you have 15 questions. So go ahead and look at the first one. Solid sodium oxide, lies. Liquid pentane is burnt in air. Let's do the first one. Number 2, we're doing the evens. Write this down in your agenda if you need to. Ready when you are. What's liquid pentane? C5H12. And I'm going to put L next to that because I'm not going to think to put liquid unless I say it, you say it up front. Burnt in air, what does that mean? So adding O2. So then you have to stop. Now that you have in your brain all these reactions that you know, what kind of reaction is this? Combustion. So think to yourself on what kind it is. It is combustion. What does combustion always make? And H2O. Generally, I think the breaking point is 3. So if it's got 3 plus carbons, it gets so exothermic and so hot, everything vaporizes. Like the carbon dioxide, you're like, duh, it's a gas. I know that. But the liquid, water, sometimes it's water vapor, sometimes water gaseous, like vapor itself. So I'm going to put gaseous water there. So knowing that's a gas, and that's gas, what's the only thing you really have to do here? Balance it, right? Okay, balance it. Do you need an NIE here? Is this in aqueous solution? There will anything ionize? No. Gas, liquid, nothing will ionize. Don't touch it after you balance it. So some of these are going to be like NIEs where you ionize. Some of them are just reactions. Now, everything has a question with it. How would you detect when the gas is formed? Do you guys remember how to detect for carbon dioxide? Say again? There's a method in the lab that you test for carbon dioxide. You can test for oxygen gas, carbon dioxide gas, and hydrogen gas that way. Say again? The popsicle, the flaming splint test. Okay, and I'll do a demo for you guys tomorrow. But flaming splint, which is just like a popsicle stick test. What happens if you put a flame to carbon dioxide? It goes out. That's how you can test. But if it's with oxygen, what happens? It burns brighter. Okay, so I'm going to leave that for you guys. You guys are doing all the evens. And then the video, you guys can keep looking at that for a minute. I'm going to show you the video on my website for pH. We get out in 3 minutes, so don't leave me, but do what you got to do. I'll tell you, your labs I won't take them up till the end of this unit. Your whole lab notebooks. Hey. Yes, I do. Hold on, give me a second. Let me pull up this homework for you guys. Hey, what's up?
I know it's not like doing number 1, but I kind of want to know how you would know what color the solution is.
Is this
I'm curious.
So if you saw in your reactions yesterday, most of those precipitates were what color?
White.
White. Most things are, unless it's a transition metal. Transition metals have special colors. Most precipitates are white, so it's really boring.
Okay.
It's actually really boring.
I thought it was going to be cool.
I know. Oh, I don't have this up there yet. That's why I can't find it. Alright, oh, not under homework. It's in the wrong spot. Alright guys, look up here for me real fast. Do you guys know where these videos are? Where are these videos found on my website? Where are they? Bottom of Doc's page. Okay, it's the first 10 minutes of pH calculations video. First 10 minutes. You can go further if you want to, but it's got more reaction prediction with NIEs if you just want some extra help with that, but I will be doing more NIEs with you tomorrow in class, okay? Just kind of peppering it throughout, because we could literally spend 5 days on the NIEs for you before this year's. So we're just going to do a little bit at a time. So you're watching this video, how many minutes? 10 minutes. First 10 minutes. Bye.